Overview and objectives. Children, we come across hydrocarbons in our day-to-day lives, but don't realize it at times. Right from the food we eat, that is carbohydrates, the dress we wear, to even the fuel that we fill in our car, cook food, etc. But what are hydrocarbons? Let's learn about these hydrocarbons in detail. Hello children. Today we will be discussing about hydrocarbons. I'm sure that you all must be aware that a hydrocarbon is any chemical compound that consists only of the elements carbon and hydrogen, and it benefits us in the field of food, clothing, housing, art, aesthetics, and as fuels, etc. We don't know anything more than this, isn't it? So in today's class, let's learn about hydrocarbons in detail. Learning objectives. In this topic, we will learn about hydrocarbons, the fundamental organic compounds, RUPAC naming concept, addition reaction, substitution reaction. Hydrocarbons. Hydrocarbons are molecules made out of hydrogen atom and carbon atoms. The simplest hydrocarbon molecule is methane, which is one carbon atom bonded with 4 hydrogen atoms. In the beginning of 19th century, scientists classified the compounds of carbon into 2 types based on their source of occurrence. Number 1. Inorganic compounds obtained from non-living matter, ammonium cyanate, inorganic compound, NH4OCN. Number 2. Organic compounds obtained from living matter, such as plant and animal sources. However, the basis of classification was subjected to alteration after Wohler synthesis. Friedrich Wohler, a creator of revolution in organic chemistry. The term organic chemistry was used by a Swedish chemist, Berzelius. This refers to the chemistry of living things. However, the German chemist Wohler succeeded in creating an organic compound, that is urea, from an inorganic compound, ammonium cyanate, in his laboratory. Modern definition of organic chemistry. Organic chemistry is defined as the branch of chemistry that deals with organic compounds which is made up of the hydrocarbons and their derivatives. It gives a thorough insight into the nature of bonding, synthesis, characteristics, and their usefulness in various fields. Carbon compounds: organic, hydrocarbon, urea, proteins, carbohydrate, fat, inorganic, CO2, CO, metal carbonates, metal hydrogen. Carbon forms a large number of compounds. So far, formulae of about 3 million carbon compounds are known. Classification of organic compounds. The organic compounds are classified on the basis of structures as follows. Aliphatic or open-chain hydrocarbons, closed-chain hydrocarbons. Aliphatic or open-chain hydrocarbons. Hydrocarbons. Number 1. Aliphatic or open-chain compounds. Number 2. Cyclic or closed-chain compounds. Aliphatic or open-chain hydrocarbons. These are the carbon compounds which have carbon-carbon long open chains which are either straight or branched. They are classified as: Number 1. Saturated hydrocarbons. Number 2. Unsaturated hydrocarbons. Straight chain or non-branched compounds. CH3 single bond CH2 single bond CH2 single bond CH3. Butane. CH3 single bond CH2, single bond CH2, single bond CH2OH, 1 butanol. CH2 double bond CH2, ethene. Branched chain compounds. 2-methyl propane, 2,2-dimethyl propane. Cyclic or closed chain hydrocarbons. These are the hydrocarbons which have carbon-carbon closed chain rings of atoms and are known as cyclic or ring compounds. They are classified as: Number 1. Alicyclic hydrocarbons. Number 2. Aromatic hydrocarbons. Saturated and unsaturated hydrocarbons. Saturated hydrocarbons. Hydrocarbons having single bond are known as saturated hydrocarbons. Saturated hydrocarbons contain carbon-carbon and carbon-hydrogen single bonds. Saturated hydrocarbons are known as alkane. These are also known as paraffin. These hydrocarbons are the basis of most petroleum products. Example: methane, ethane, propane, etc. General formula: CnH2n plus 2. If n is equal to 1, then CnH2n plus 2 is equal to C1H2 multiplied 1 plus 2, that is equal to C1H4, that is equal to CH4. Name of this compound is methane. Unsaturated hydrocarbon. Hydrocarbons having one or more double or triple bonds between carbon atoms is called unsaturated hydrocarbons. Hydrocarbon with double bond. Hydrocarbons having at least one double bond are known as alkene. Example: ethene, propene, butene, etc. General formula of alkene: CnH2n, where n is equal to number of carbon atoms. If n is equal to 1, therefore CnH2n is equal to C1H2 multiplied by 1, that is equal to CH2. Name of this compound, since hydrocarbon having one carbon atom, is known as methane. Thus, methane minus ane plus ene is equal to methane. But alkene does not exist with one carbon atom, thus methane does not exist. If n is equal to 2, therefore CnH2n is equal to C2H2 multiplied by 2, that is equal to C2H4. Name ethane minus ane plus ene, that is ethene. If n is equal to 3, therefore CnH2n is equal to C4H2 multiplied by 4, that is equal to C4H8, that is equal to butene. In similar way, other alkenes are formed. Hydrocarbon with triple bond. Hydrocarbons having at least one triple bond are known as alkyne. Example: ethyne, propyne, butane, etc. General formula of alkyne: CnH2n-2. Similar to alkene, minimum 2 carbon atoms are necessary to form triple bond between them. If n is equal to 2, therefore CnH2n-2 is equal to C2H2 multiplied by 2 minus 2, that is equal to C2H2, that is equal to ethyne. If n is equal to 3, the compound is called propyne. Therefore, CnH2n-2 is equal to C3H2 multiplied by 3 minus 2, that is equal to C3H4, that is equal propyne. If N is equal to 4, the compound is called butyne. Therefore, CnH2n-2 is equal to C4H2 multiplied by 4 minus 2, that is equal to C4H6 is equal to butyne. Alicyclic and aromatic hydrocarbons. Alicyclic hydrocarbons. An alicyclic compound is an organic compound that is both aliphatic, that is do not have benzene ring in their structure, and cyclic. They contain one or more all-carbon rings which may be either saturated or unsaturated, but do not have benzene ring in their structure. Some of the examples are cyclopropane and cyclobutane. Cyclopropane, cyclobutane, cyclohexane. Aromatic hydrocarbons. These are the hydrocarbons which have benzene ring in their structure. When hydrogen bonded to carbon of benzene is substituted with halogens, radicals or other functional groups, the derivatives are called aromatic compounds. Aromatic compounds are called so because many of them possesses a fragrant smell. Greek word aroma means sweet smell. Benzene, monocyclic. Naphthalene, biocyclic. IUPAC name of hydrocarbon. According to IUPAC system of nomenclature, the name of an organic compound consists of a root word, a suffix, and a prefix. Root word. It is the basic unit of the name. It denotes the number of carbon atoms present in the principal chain. That is the longest possible continuous chain of carbon atoms, including the functional group and the multiple bonds of the organic molecule. For chains from 1 to 4 carbon atoms, special root words that is based upon the common names of alkanes are used, but for chains of 5 or more carbon atoms, Greek number roots are used. Extra A given in parenthesis used only if the primary suffix, explained later, to be added to the root word begins with a consonant. In general, the root word for any carbon chain is ALK, that is L. Suffix. There are 2 types of suffixes. Number 1. Primary suffix. A primary suffix is always added to the root word to indicate whether the carbon chain is saturated or unsaturated. If the parent carbon chain contains 2, 3, 4 or more double or triple bonds, numerical prefixes such as di for 2, tri for 3, tetra for 4, etc. are added to the primary suffix. For example, types of carbon chain: unsaturated with 2 double bonds. Primary suffix diene. General name alkadiene. Types of carbon chain: unsaturated with 2 triple bonds. Primary suffix diene. General name alkadiene. Extra A has been added to the root word since the primary suffix, that is diene or diene, begins with a consonant. That is D instead of a vowel, as in the case in the first 3 examples. Number 2. Secondary suffix. A secondary suffix is then added to the primary suffix to indicate the nature of the functional group present in the organic compound. It may be noted that while adding the secondary suffix to the primary suffix, the terminal E of the primary suffix, that is ane, ene, and ine, is dropped if the secondary suffix begins with a consonant. The terminal E from the primary suffix has been dropped because the secondary suffix begins with a vowel. Number 3. Prefix. There are 2 types of prefixes. Number 1. Primary prefix. A primary prefix is used simply to distinguish cyclic from acyclic compounds. For example, in case of carbocyclic compounds, cyclic compounds containing only carbon atoms in the ring, a primary prefix cyclo is used immediately before the root word. Thus, cyclo, which is primary prefix, pent, root word, ane, primary suffix, cyclopentane, IUPAC name. If the prefix cyclo is not used, it simply indicates that the compound is acyclic or open chain. Number 2. Secondary prefix. In IUPAC system of nomenclature, certain groups are not considered as functional groups but instead are treated as substituents. These are called secondary prefixes and are added in order to denote the side chains or substituent groups. Thus, a complete IUPAC name of an organic compound consists of the following parts: secondary prefix plus primary prefix plus root word plus primary suffix plus secondary suffix. IUPAC rules for naming hydrocarbons. Select the parent carbon chain. Number 1. Select the longest continuous carbon chain as the parent chain. If a double or a triple bond is present in the carbon chain, it should be included in the parent chain. Number 2. If a functional group is present, the carbon chain should include the functional group. Number the parent carbon chain from that carbon end such that the functional group, double bond, triple bond, or side chain gets the lowest number. Number 1. Remember here that the aldehyde and carboxylic acid functional group are present on the terminal carbon atom. Identify the name and position of the functional group, double bond, triple bond, or side chain. The name of the functional group is written with either a prefix or a suffix as given in the above table. If the name of the functional group is to be given as a suffix, the name of the carbon chain is modified by deleting the final E and adding the appropriate suffix. For example, a 3-carbon chain with a ketone group would be named in the following manner. Propane minus E is equal to propane plus one is equal to propanone. Remember that in the compounds which have carbon-containing functional groups, the name of the root word includes the functional group carbon atoms also. If the carbon chain is unsaturated, then the final ane in the name of the carbon chain is substituted by ene or ine as given in the table above. For example, a 3-carbon chain with a double bond would be called propene, and if it has a triple bond, it would be called propyne. Remember, if the hydrocarbon is an alkane, the position number of suffix is not written. Naming side chains. Click each to more information. Correct ending. The longest carbon chain. Number to each carbon. Attach prefix according to number of carbons. 1 hexene. Determine name for side chains 1 hexene. Attach name of branches alphabetically. 2-ethyl, 4-methyl, 4-methyl, 1-hexene. Group similar branches. 2-ethyl 4, 4-dimethyl 1-hexene. Homologous series. A series of organic compounds in which every succeeding member differs from the previous one by CH2 or 14 unit. The molecular formula of all the members of a homologous series can be derived from a general formula. CH4 and C2H6, these differ by a CH2 unit. C2H6 and C3H8, these differ by a CH2 unit. Properties of a homologous series. As the molecular mass increases in a series, so physical properties of the compounds show a variation, but chemical properties which are determined by a functional group remain the same within a series. Homologous series, alkanes. General formula, CnH2n plus 2, n greater than or equal to 1. Example, CH4, n is equal to 1. Functional group, no one. Homologous series, alkenes. General formula, CnH2n, n is greater than or equal to 2. Example, C2H4, n is equal to 2. Functional group, C double bond C. Homologous series, alcohols, alkenols. General formula, CnH2n plus 2 O, where n is greater than or equal to 1. Example, CH4O, n is equal to 1. Functional group, OH. Homologous series, carboxylic acid or alkanoic acids. General formula, CnH2nO2, where n is greater than or equal to 1. Example, CH2O2, n is equal to 1. Functional group, COOH. N represents the number of carbon atoms. Homologous series of alkanes. General formula, CnH2n plus 2, where n is equal to number of carbon atoms. Homologous series of alkenes. General formula, CnH2n, where n is equal to number of carbon atoms. Homologous series of alkynes. General formula, CnH2n minus 2, where n is equal to number of carbon atoms. Functional group. An atom or a group of atoms which when present in a compound gives specific properties to it, regardless of the length and nature of the carbon chain, is called functional group. A. Free valency or valencies of the group are shown by the single line. B. The functional group is attached to the carbon chain through this valency by replacing one hydrogen atom or atoms. C. Replacement of hydrogen atom by a functional group is always in such a manner that valency of carbon remains satisfied. D. The functional group replacing the hydrogen is also called as heteroatom because it is different from carbon and can be nitrogen, sulfur, or halogen, etc. Heteroatom. Chlorine, bromine. Functional group, halo, chloro or bromo. Formula of the functional group, Cl, suffix, named as prefix, chloro, bromo. Heteroatom, oxygen. Functional group, alcohol. Formula of the functional group, OH, suffix, OL. Functional group, aldehyde. CHO, suffix, AL. Ketone, CO, suffix, ON. Carboxylic acid, COOH. Oic acid. Addition and substitution reaction. Addition reaction. Addition reaction is the one in which a molecule adds across a double bond or a triple bond. C double bond C plus AB gives Ca single bond Cb. Unsaturated hydrocarbons undergo addition reactions. Hydrogenation reaction involves the addition of hydrogen to unsaturated hydrocarbons in presence of catalyst like nickel to form saturated hydrocarbons. CH2 double bond CH2 gives, in presence of nickel and hydrogen, CH3 single bond CH3. This reaction is commonly used in hydrogenation of vegetable oils using a nickel catalyst. Number 2. Substitution reaction. A substitution reaction involves the replacement of an atom or group of atoms by other atom or group. Alkanes undergo substitution reactions. For example, chlorination of methane in presence of sunlight gives a mixture of products like methyl chloride, methylene chloride, chloroform, and carbon tetrachloride. CH4 plus Cl2 in presence of sunlight gives CH3Cl plus HCl. CH3Cl plus Cl2 in presence of sunlight gives CH2Cl2 plus HCl. CH2Cl2 plus Cl2 in presence of sunlight can give CHCl3 plus HCl. CHCl3 plus Cl2 in presence of sunlight gives CCl4 plus HCl. Summary. Students, we have come to an end of our discussion on hydrocarbons. Just revise the lesson for tomorrow, and if you have any doubts, I'll explain it. Children, we have just finished listening to the explanation given by our chemistry sir on hydrocarbons. Hope you all have followed his explanation well. Bye.